Hey everyone! So this is lesson 2.2 and we're going to be getting into operations with vectors. So when I say operations, I'm talking about like vector addition, vector subtraction, scalar multiplication, and so on. But I don't really want to get into it until we review a little bit because I want to make sure your foundation is pretty solid. All right, so let's do a little bit of review. On the right hand side, we have a coordinate. Now, if I decided to make that coordinate a position vector with the origin, I could call it OV, or I'm just going to call it V, and written in the ordered pair, it would look like this. Okay, so it looks very much like a coordinate. If I wanted to write it in terms of its unit vectors, we call that basis vector form. So here is my horizontal unit vector and my vertical unit vector. And so we have 3 horizontals, right, because it's a 3x, and 4 verticals because it's a 4 for your y. Okay. Now, writing a unit vector, that's not v like this, okay? It's actually v like this. Basically, what I want to do is I want to manipulate the position vector for v into something where my v magnitude would equal to 1. Okay, that's what makes it a unit vector. So this is the way that we're going to do it. There is a formula, and that is taking your vector v and multiplying it by 1 over its magnitude. So I did show you something like this in a previous video, but it's always good to just review. Okay, so that's 3 and 4, that was your vector v. 1 over, now to find the magnitude, you take each of your components, so your 3 and your 4, you add them together after you square them. Okay, so basically taking like the Pythagorean theorem of each of your components. Let's move this so I have a little bit more space. Okay, so 3 squared plus 4 squared, that should give you 25. Square root of 25 is 5. Okay, so I get 5 in the denominator, and then I still have to multiply that vector. Distribute the 1/5 into the brackets, and I get 3 over 5 for my x component, 4 over 5 for my y component. And this is not v like this, it is your unit vector v. Which means that if I decided to find the magnitude, it should equal to 1. So let's just check this. All right, let's find the magnitude. Whoop, I did not write that right. You got to write it with the hat, like that. Okay. Take each of the components, square them, add them together, and square root them. So Pythagorean theorem. That's going to give me 9 over 25, 16 over 25, which is 25 over 25, and you already see it. It's going to equal to 1. Okay, so we've found our unit vector v from our vector v just by multiplying the reciprocal of the magnitude of vector v. Okay, so that's a little bit of review. Let's get into some new stuff. All right, let's pretend that you have 2 vectors. You got one in red and one in blue. It looks like each of those vectors is in 3 dimensions because there's 3 components. It also looks like what I just underlined is in the coordinate form. Okay, so the ordered triple in this case, whereas the ones down here are in the basis vector form. Okay, so whether it's in one form or the other form, it really doesn't matter. They mean the same thing. But what this general box is saying is that if you know that the red vector is equal to the blue vector, that must mean that its x components are equal. The y components are equal, and the c components are equal. Okay, that makes sense, right? I'm going to go into vector addition and then a little bit of vector subtraction. Okay, so when we do addition, vectors are still going to follow the same kind of rules that polynomials generally follow, which are commutative, associative, and distributive properties. Okay, so let me show you. Let's do this in 2D or r squared first. I'm going to give you 2 vectors, vector u and vector v. Okay, so you can already see that these are in 2 dimensions because you have 2 unit vectors inside, your I and your j. If I want to add the red and the blue together to find a resultant vector, u plus v, I'm going to add them in the next line. Okay, so notice that I keep it in brackets just to make things, obviously you're not writing all this stuff in pencil crayons. So for yourself, since you're writing in pencils, make sure that you put your brackets. It shows your teacher that you're adding those 2 vectors separately. Now in the next step, because you want to combine them, take all the brackets off. Okay, it doesn't really change anything, just like in polynomials. And then combine any like terms. So notice that with the I vector, there was an a, which is a coefficient, and you're going to add it with c, which is another coefficient. Okay? Plus, your b and your d are in front of your j vectors. So b and d could be like regular numbers like 2 and 5, but j will be a vector. Okay, so b and d will combine to make the coefficient that goes in front of your j unit vector. So that's pretty messy. I like actually writing it in the coordinate form instead. And so in the coordinate forms, all you do is you take, instead of the i's and j's, you just leave all that out and you write down the 2 components, your a and your b, or your c and your d. Okay, so adding those 2 together, take your 2 x components and add them together, and then take your 2 y components and add those together. So it's still written as a vector. Okay, so you need your brackets and you need your comma because it's going to be the resultant vector of adding u and v together. Now let's take a look at 3D. Pretty much the same thing. You're taking your red u, adding it to your blue v. Okay, so underneath I have everything in brackets. Then you're going to strip them of their brackets and put together anything you can. So a and d are going to give you the coefficient for your I vector. Then you got b and e with your j vector. And then you got your c and f for your k unit vector. Okay, so that's basis vector form. And then you're going to put them on the right-hand side. We're going to take a look at the ordered triple form, adding the x components, a plus d, adding the y components, b and e, and then the z components, c and f. Okay, so that's addition. Let's try an example. I'll get into vector subtraction in a little bit. Okay, so example number 1. Find q, r, and t if they give you 3 vectors adding together to equal another vector. Okay, so the first line I just rewrote the question, and now I'm going to try to solve for q, r, and t. So you'll notice that each of the x components, when I add them together, they should equal to 5. Okay, any of the y components, if I add these guys together, they should give me -2. All right, and any of the z components over here, adding together should give me a 7. So that's essentially what I wrote in the next step. I put all the reds together into the x component, all the y's together as the middle component, and then all the z's together as the last component in order to make it look like the answer. So the answer is a vector with brackets and commas. Make sure that the left-hand side, like all of this, also has brackets and a comma. Okay, solving each one. Make the x component equal to 5. And then solve for r. Making the blue component equal to -2, solving for q. And then making that last component equal to 7 and solving for t. So r is 2, q is -6, and t is 0. Okay, so that's just an example of vector addition. Let's take a look at vector subtraction. Okay, vector subtraction is something that we use when we want to find a vector between 2 points. So let's just say this is point P and this point Q. If I wanted to find a vector from one to the other, I would use subtraction. I would actually take Q, the one that you're trying to get to, and I would subtract P. Okay, so whatever is the second one, that's the one that goes first. So C is going to subtract A in order to get your X component. All right. D is going to go and subtract B. So you're going to start with the Q point minus the P point, and that's going to give you your next component. Same thing if you have it in 3 dimensions. So Q minus P, Q minus P, Q minus P. All right? And you're going to ask, well, why subtraction? Why do we do it backwards? Let me show you through this example. Let's say that we have two coordinates. Okay, so here's A, and that's right here. Okay, 3, whoops, I'm a little bit off. Right here, and that's going to be A at 3, 0. But I could create a position vector with the origin. Then we have B at 7 and 5. 7 to 5 is like right here. And again, I can create a position vector with the origin. Okay? Now, if I wanted to create AB, because that's what they're asking you to find, they want you to find AB. Well, why don't we join A and B together like that? And we could always say, well, it looks like the red vector plus the black vector equals to the blue vector, because OA, that's O, plus AB is equal to OB, right? Like OB is a resultant of the two black and red vectors added together. So that's what I've written here. Oh, did I make a weird line? That's okay. I'm a little bit messy. Okay. What I can do is I can solve for AB by moving this guy over to the other side, and it becomes a negative. So notice that in order to find AB, I'm subtracting B and A in that specific order. And that's why you take whatever the second letter is first, subtract the first letter. So if I were to write this out, and just for like space, I'm going to do this in the ordered pair notation. Okay, take your B, which is 7, 5, subtract your A, which is 3, 0. Okay, so you got B minus A. Now what you're going to do is you're going to subtract the numbers. Okay, so 7 minus 3 and 5 minus 0. So AB is going to be a vector with a 4 as your horizontal component and a 5 as your vertical component. And let's just take a look. I mean, I think it actually works. If you start at 3 and you go towards, like we want to make like a right angle triangle, okay? It looks like from 3 all the way to 7, isn't that like 4 units long? Okay, and then from the height of 0 all the way up to here, that's 5 units long. And so those two, your horizontal and your vertical, make up the resultant, which is your AB vector. Okay, now going into scalar multiplication. This one's a little bit more intuitive. Okay, so scalar multiplication is if you have a vector, 3D, 2D, whatever, and you have a scalar number, so some sort of a constant, in front of that vector, you can multiply it in and multiply it with any of the other constants or coefficients that are inside that vector. Okay, so, or I shouldn't say the vector, I should say inside the brackets. So you're going to get k times the other coefficient a, but then with the vector on the outside, which is vector I. If you decide to write it in the coordinate form, same thing, k times a, k times b. Remember to put it still in a coordinate form. So if you have 3D, okay, a 3D vector, and you also have some sort of a constant, just multiply it in. Okay, so let's take a look at a type of question. I have vector t, so this is example number 3 now, and I have u. Okay, those are two 3-dimensional vectors, and I want to find q, but q is made up of 3 t's minus 2 u's. Okay, so what I'm going to do is I'm going to take 3 times the t vector, which I have in red, minus 2 times the blue vector, which is your u. Okay, and now I'm going to simplify. I'm going to take the 3 and distribute it in, but keep it as like a vector. 12, 6, negative 15. The reason why is because it's going to look really weird if you just have like commas in between numbers and subtract signs. Like it just looks kind of weird without the brackets. Okay, now this part is up to you. You can put minus and just do the 2 in, okay? And you would get something like this, 6 and 14. If you don't want to and you want to put the entire negative 2 in, this would be a positive. Okay, so your first number would be like a positive 2, negative 6, and negative 14. You can do it either way, whichever way you want. So why don't we just continue this way? Let's add them together now. Take the x components. 12 plus 2 is 14. 6 plus negative 6 is going to give you a 0. Negative 15 plus negative 14 is negative 29. So that's going to be the vector q. All right, the very last part, which is collinear. Collinear essentially means they're on the same line. Okay, so they're on the same straight line, I should say. What you're going to do is you're going to make sure that you put them together as 2 vectors. So PQ, I'm going to put together like this, and QR, I'm going to put together like that. And I kind of want them so that they're consecutive. So I'm hoping that P to Q and Q to R are along the same lines if they have the same ratio. Okay, so they're scalar multiples of each other. Now, what does that mean? I'm going to show you. Okay, to find PQ, I'm going to take Q, because it's a second letter, right? Take Q, and I'm going to minus P. All right, so I have that down on the left-hand side, and let's figure out the answer. So I got 2 minus 1 is 1, 4 minus 3, which is 1, 5 minus 4 is also 1. Okay, now I want to find QR, and I'm going to compare it to PQ. So QR starts off with, I really should have done this in green. Why don't we change this so that this matches? I'm going to make this green, and let's also make this guy green. I like to match it just in case you guys are following my colors. I don't know if you guys follow my colors, but I find that it helps. Okay, so we got this guy in green. Start with the R because R comes second when you're trying to find QR. Take R minus Q, and you're going to get 4 minus 2 is 2. 6 minus 4 is 2. 7 minus 5 is also 2. Notice that when we compare both of the answers, this guy on the left-hand side is equal to 1/2 QR, right? It's just a half. Like if I took QR, the 2, and the 2, and I took a half of all of them, I'm going to get 1, 1, 1. Simultaneously, this is also double PQ, because PQ was 1, 1, 1. If you double it, you're going to get 2, 2, 2. This is what I mean by scalar multiples. Essentially, they're the same, but they're different multiples of each other. And if they are scalar multiples, then we're going to say, therefore, all 3 of the coordinates are collinear. Okay, so scalar multiples. Okay. The last question, example number 5. Okay, so they've given us A, which is 5, 5, and I have that right here. That's my A. Notice that I've already made my position vector. I have C, okay, which is at 3 and negative 2. That's this guy right here, position vector C. Okay, and what I want to do is I want to figure out what B is, and it makes a parallelogram, and the parallelogram is called OABC. So OABC. C. Just make sure that like you go in the circular order when you actually answer it, and you don't go O, A, B, C, like something weird like that. Okay? If this makes a parallelogram, I mean, obviously, because we have the grid, we can kind of figure out where B is. It's probably somewhere around this area to make like our parallelogram, but I don't want you guys to guess, and so we're going to use algebra in order to figure it out. OB should equal to OA plus AB. Okay, so when I say that, I mean B, which is probably going to be, I mean, shouldn't it be parallel to this? Right? Like in the same general direction, like that. So I'm guessing that it's probably here. Okay, but let's just take a look at the first part that I had written down. OB, which is this guy, is going to be equal to OA, which is red, plus AB, which is green. So that's what I said again right here. Now I'm going to solve for this. The green and the blue vectors are exactly the same. So I'm just going to replace this guy and put the blue instead, because the blue one I actually have numbers for. It's right here in the question. I don't have the green numbers, and therefore I can't really use it. Okay, so since I have the red numbers and I have the blue numbers, I'm going to sub them in. Red is 5, 5, blue is 3 and negative 2, and we're just going to add them together, and we get 8, 3. So is that where it is? Yeah, actually that is where it is. See, 8 and then 3, right? Okay, so therefore, the coordinates of B are 8 and 3. Okay, so that gets into the operations with vectors. And what we're going to be doing in the next lesson is, what are we doing in the next lesson? I don't even know. We're going into dot product. Okay, that one's going to be a little bit interesting. All right, stay tuned, guys.